Today we are going to start February-March 2023, paper 5-2. Let's start with question number 1. Aqueous in acidic conditions to prevent them readily oxidizing to aqueous iron 3 ions. Okay. So it means that in acidic conditions, iron 2 positive ions does not oxidizes to iron 3 positive when there are acidic conditions. Iron 2 positive ions react with silver ions in a redox reaction. The following equilibrium is established. Okay. And here we are getting silver on the product side as a solid. The concentration of Fe2 positive aqueous at equilibrium can be found by titration with the standard solution of aqueous potassium manganate 7, KMnO4. KMnO4 aqueous is deep purple in color. The equilibrium constant for the reaction can be found using the following equation. So here you have an equation, and equation it is same as Kc expression that you have did in your AS syllabus as well. The only thing, if you look over here, they have written EQM, and that EQM is actually referring to equilibrium, which means that we use the concentrations over here are actually. Is this clear to everyone?
Hello, Assalamu alaikum,
Yes.
sir.
Just give me a minute, please. Okay. Now let's have a look at the method. A student carries out the experiment using the following instructions. At 100 centimeter cube of 2 mole per dm cube silver nitrate. So here we have the volume of silver nitrate and the concentration of silver nitrate. 200 centimeter cube of 0.2 mole per dm cube iron 2 nitrate. So here I have a volume and the concentration of iron 2 nitrate. In 500 centimeter cube conical flask, and stopper the flask. Label the conical flask A. Okay. Leave conical flask A for 4 hours, shaking intermittently. Then leave conical flask A untouched for 1 hour. So it means for 4 hours we do the shaking in between, and then after that 4 hours have passed, we left the conical flask for 1 more hour, and in that one more hour it stays untouched. Okay. Now in step 3, use a pipette to transfer 25 centimeter cube of a solution from conical flask A into a clean 250 centimeter cube conical flask. Label this conical flask B. Okay. Now add 5 centimeter cube of 1 mole per dm cube sodium chloride aqueous to the solution in conical flask B. A white precipitate of silver chloride forms. Yes, because it have a silver nitrate in the solution, right? And if there are silver ions and we have added sodium chloride, so sodium chloride, the silver ions from the mixture which are at the equilibrium reacts with the chloride ions to form silver chloride solid, which are of white precipitates. Okay. Is this understandable to everyone till here? Till step 4, is this clear to everyone?
Yes, sir.
Now, use a measuring cylinder to add 20 centimeter cube of 1 mole per dm cube sulfuric acid to a conical flask B. Okay. So after the precipitates had formed, what we did, we used this volume and this concentration of sulfuric acid when we have added to conical flask B. Rinse a burette and fill it with a standard solution of potassium magnate. Add potassium magnate to the mixture in a conical flask B until an endpoint is reached. So remember, I have discussed earlier, whenever we are using KMnO4, potassium magnate in burette, right, and doing the titration, then the color change of the endpoint would be always colorless
Pink
to
solution, sir.
Colorless.
pale pink. Okay. Now, empty conical flask B and rinse it with just water and ready for the next titration. Okay. The important readings, the readings which have at least two readings having a difference of 0.1 centimeter cube. Then those are considered as a concordant readings. Okay. Is the method is clear to everyone? If anyone have any doubt in the method, do ask. Okay. The student records their results in table 1.1. Part 1 is saying you have to complete the table 1.1. Okay. So to complete the table, you have to take the differences. Here, it would be 10.50. If you subtract these two, 19 minus 10 would give you 9. So 9.65. Here, it would be 0 and 12 minus 3, 9. And 29 minus 20, 9.90. And here, 5, 7, and 9. So you have to subtract these two values to find the titer. So titer is the volume that is, added in the conical flask to reach the endpoint. Now, calculate a suitable mean titer to be used in the student's calculation. Show clearly how you obtain the mean titer. Okay. So the mean titer, to find the mean titer, we choose only two readings except the rough one. We do not include the rough one. Beside the rough one, if you have a two readings which have a difference of 0.1 centimeter cube, so it means that titration 1 and titration 3 can be used to find the mean titer. So you can write over here that titration 1 and 3 and the volumes are over there would are 9.65 plus 9.75 divided by 2. So if you divide them, the average volume that you got over here would be 9.70. Is this understandable to everyone? Yes. Okay. Now, in part B, they are asking state what is meant by the standard solution in step 6. So I have discussed that thing earlier as well. it is a solution whose concentration is known. So you can write a solution of known concentration. Just give me a minute, please. Okay, so remember, whenever the examiner asks you about the standard solution, so that standard solution is any solution of a known concentration. Is this clear to everyone? Yes. Suggest why conical flask A is left for 4 hours in step 2. Yes, anybody can suggest why we did this.
To let the
That
reaction
the
complete.
conical flask is left for let the reaction complete. Are you sure? Look at the equation.
To let the reaction reach equilibrium position.
Yeah, to let the reaction reach equilibrium position, because it's a reversible reaction. So if you write to let the reaction complete, it would be wrong. So to let the reaction reach equilibrium. Suggest why conical flask A is not shaken during the final hour in step 2. Yes. Okay, look at the equation and these steps till step 2. In the reaction mixture, there is a solid as well, right? So for the last 1 hour, we keep it untouched to make sure that all the solid must be settled down. Otherwise, because see, we are taking from the flask A, we are taking out this 25 centimeter cube into a flask B. So if the solid must not be settled down, then in flask B, we must have the solid particles of the silver as well. So that's why we keep it for 1 hour untouched. Okay. So let the solid settle at bottom or settle down. Is this understandable to everyone?
सर आप ये एक बार फिर रिपीट कर देंगे.
See, there is a solid over here, right? So we have to transfer the 25 centimeter cube into flask B from flask A. So if we don't left it for 1 hour, then the solid would be, would not be settled down at the bottom, and there is a chance that we may contain the solid in flask B as well.
Okay, sir. Got it.
Is this clear to everyone?
सर पर इनिशियली हम क्यों चेक कर रहे थे?
Sorry?
Like initially जब हमने for this hour इसके लिए क्यों चेक कर रहे थे?
Yes, initially we when we mix it, what is our objective is to establish the equilibrium, right?
Right.
So if we are shaking it, that shaking is for the purpose that we want to reach the equilibrium as soon as possible.
Right.
Is this clear now?
Yes, sir.
Okay. Just give me a minute, please. Okay. So for the final hour, we didn't shake it. It is because we allow the solid to settle at the bottom. Now, part D suggests why a measuring cylinder is most appropriate apparatus to use for measuring sulfuric acid in step 5. Yes. Normally, if you remember, whenever we use the measuring cylinder, it is for the reactant which is actually in excess. So there is no accuracy needed. There is no accuracy needed uh, for that when the reaction mixture is in excess. Okay. So here we would mention that acid is in excess. Okay. Now, can anybody tell me the reason why we would edit the acid in excess? Yes, can anybody identify why we would adding acid in excess?
Try to reach the end point.
No. Initially, see in this paper they didn't ask, but they might ask about this. If you see at the start of the reaction, they have informed you. See the first statement that when we keep the acidic condition, then the iron 2 positive ions does not oxidize to iron 3 positive ion. So obviously, so for that purpose, that we have to prevent the iron 2 positive ions did not oxidize into iron 3 positive ions. That's why we are adding acid in the excess. So there would be no error in finding the concentration of iron 2 positive ions at equilibrium mixture. Is this clear to everyone?
Yes.
Yes.
Yes, sir.
Okay. Now, state what the burette should be rinsed within step 6. In step 6, burette is filled with standard solution of KMnO4 aqueous, right? So this is the way that when we are filling a chemical in the burette, then we would rinse the burette with the same chemical. So here we would write that uh, KMnO4 aqueous is used to rinse the burette. Is this clear to everyone?
Yes.
Okay. Now, state the change of color seen in mixture in conical flask B at the end point of step 7. So we have already discussed it that whenever the potassium magnate is in, burette, then the end color is pale pink, and normally the initial color in the conical flask is colorless. The student repeats the experiment using KMNO for aqueous at lower concentration. The student obtains a larger mean titer. Suggest one reason why a larger titer is better than the smaller titer. So what it is saying that when the lower concentration of potassium magnate is used, then what would happen? That this volume would be smaller. Oh, sorry, this volume gets greater. For example, if your initial reading is 0.10 and we have using the lower concentration of KMNO4, so let's say it would be 20.60 now, the titer volume, the final titer. So what is the advantage of using the lower concentration when the volume gets bigger?
Percentage error decreases.
Very good, Safiullah. That by increasing the, by lowering the concentration, what would happen? Now we are getting the, we are consuming the more volume. So if we are consuming the more volume, then if you recall how to calculate the percentage error, the error would be the same, but the volume that we used gets greater. So obviously the percentage error would decrease. Is this part is clear to everyone?
Yes, sir.
Now each part. The equilibrium is shown. When another student carries out titration with 0.02 mole per dm cube potassium magnate, the mean titer is 21.10 centimeter cube. So here is the volume and this is the concentration. The ionic equation for the reaction between magnate aqueous ions and iron 2 positive aqueous ion is shown. Calculate the concentration of iron 2 positive aqueous ions in the equilibrium mixture. Okay. So we know the moles of, we have to calculate the moles of KMNO4 because we know the concentration of KMNO4 and we know its volume as well, right? So, and remember, you have to convert the volume into decimeter cube. So the concentration of potassium magnate is 0.0200 times its volume, which is 21.10 divided by 1000. Yeah. So can anybody tell me the answer, please? Yes, can anyone tell me the answer, please?
4.22 into 10 to the power minus 4.
4.22
22 into 10 to the power minus 4.
minus 4.
Yes, sir.
Okay. So we got the moles of KMNO4. Now we have to find the moles of iron. So if you look at their ratio, that 1 mole of KMNO4 is reacting with 5 moles of iron 2 positive ion. So to find the moles of iron 2 positive ion, what we can do? We can multiply the moles of KMNO4 with 5. So if I multiply the moles of KMNO4 with 5, because the ratio is 1:5, so we get the moles of iron 2 positive ions. So 5 times minus 4. What will be the answer now?
2.11 into 10 to the power minus 3.
2.11 into 10 raised to the power minus 3 are the moles of iron, right? And we have to find the concentration of this iron. So if you recall, the reaction mixture that we used in which the iron is present is 25 centimeter cube, right? So to find the concentration of iron to positive ions, we take these moles that we have found, that is 2.11 exponent minus 3 divided by 25 over 1000. Yes, can anybody tell me the answer, please?
Zero point 0.0844.
0.0844. So here we got the concentration of iron to positive ions, that is 0.0844 mole per dm cube. Yes, is this part is clear to everyone? Yes.
Yes, sir.
Yes, sir.
Okay. Now these moles of the iron are the ones which actually reacted with potassium magnate, and we have added the potassium magnate when this equilibrium is established, which means these are the more concentration of iron at when the equilibrium is established. Then this is the concentration of the iron in the equilibrium mixture. Is this understandable to everyone?
Yes, sir.
Okay. Now next part. Suggest why it is not necessary to measure the concentration of Ag positive ions in the equilibrium mixture experimentally. Yes, who can answer this part? You can take the help from the chemical equation as well. What is the mole ratio of these two? Iron 1 positive ion, silver 1 positive ion, and iron 2 positive ions.
Sir, 1 to 1.
1:1. So it means it is exactly same as the concentration of iron 2 positive ions. So I can write that it is exactly same as the concentration of iron 2 positive ion at equilibrium. Now third part, determine the decrease in concentration of iron 2 positive ions from the initial solution, hence determine the concentration of iron 3 positive ions in the equilibrium mixture. Okay, if you were unable to obtain your answer in H1, use this concentration. This is not the correct answer. Okay, so this is the concentration of iron at equilibrium, right? And I think we are with the initial concentration of iron. So what is the initial concentration of iron?
0.2.
0.2. Okay. So how we will find the concentration change? Yes. There is one, you know, there is this question is little tricky over here, because if you see over here, the initial concentration is 0.2 and its volume is 1 centimeter cube, and we are we have mixed that volume with 1 centimeter cube of silver nitrate as well, right? And the concentration of this volume, the silver nitrate is 0.2. So see, the concentration is 0.2, but when the reaction mixture is prepared, in that reaction mixture, the total volume turns it to be 200 centimeter cube. So if the total volume gets double, then it clearly means that the concentration would get half, because the total volume is doubled by adding some other reactant which doesn't contain any iron 2 positive ion. So initially the whatever the moles of iron are there will spread it in the 100 centimeter cube volume, but when the two solutions are mixed, these moles of iron 2 positive ion is actually mixed in the total 2 centimeter cube volume, 200 centimeter cube volume, which causes the concentration to be decreased by half. So first what you will do over here, that initial concentration of iron 2 positive ion in the reaction mixture would become 0. It was 0.200 divided by 2, which gives me 0.100. And now you have to find the decrease in concentration. So decrease in concentration of iron 2 positive is equal to 0.100 minus 0. What answer we have got? 0.844. So can anybody subtract and tell me the answer, please?
0.0156.
0.0156. So these are the moles of iron 2 positive which are consumed. And if you look at the equation, the mole ratio between the iron 2 positive ions and the iron 3 positive ion is also 1:1. So it means the number of moles of iron that is, or the number of mole, or the decrease in the concentration of iron 2 positive ion would be equal to the increase in the concentration of iron 3 positive ion. So initially there is no iron 3 positive ion in the equilibrium mixture. Then at
Sir,
equilibrium,
concentration is 0.02. You wrote 0.2.
okay, thank you. So 0.0200, and here I would get 0.0100. So here I would get 0.01 minus 0.0. No, it's 0.2. Check again. It's not 0.02. Yeah. So this is the decrease in the concentration of iron 2 positive ion. So the mole ratio of iron 2 positive ion and the iron 3 positive ions are exactly 1:1. So it means the concentration that is decreased from iron 2 positive ion would be the concentration of iron 3 positive ion that are formed at equilibrium. So here I will write 0.0156. Is this clear to everyone?
Yes, sir.
Now, what they are asking, determine the value of Kc, include units in your state symbol. So Kc is equal to concentration of iron 2 positive ion. If you look at, concentration of iron 3 positive ions divided by concentration of iron 2 positive ions times concentration of silver ions. So the concentration of iron 3 positive ions at equilibrium is 0.0156 divided by, here we got the concentration of iron 2 positive ions at equilibrium, which is 0.0844. And we have discussed that the concentration of silver ions would be exactly the same. So 0.0844 times 0.0844. And this Kc expression is given at the start of the question here. So Can anyone solve it and please tell me the answer?
Sir, 2.19.
So Kc is 2.19 and you have to find the concentration, oh sorry, the unit. So in numerator we have a mole per dm cube and in denominator we have a mole per dm cube times mole per dm cube, right? So these two would be cancelled out and we are left with 1 over mole per dm cube, which turns into mole inverse and dm cube. Is this clear to everyone?
Yes, sir.
Yes, sir.
Okay. Now let's move to the question number 2. Reaction in iodide ions and aqueous hydrogen peroxide ions takes place in acidic condition. Okay. See, this is acidic condition and here we have a chemical equation. A student carries out a series of experiments to investigate the order of reaction with respect to the concentration of iodide ions. The student does this by measuring the time taken for a fixed amount of iodide ions to form. Okay. So we have to investigate the order of reaction with respect to the concentration of iodide ion, right? The student and for this purpose, what a student did, student have found, find the fixed or the constant amount of iodine in each experiment, that how much time it is taken by that exact amount of iodine to be formed. A known amount of aqueous thiosulfate ions in the reaction mixture react with iodine, aqueous iodine formed in reaction 1. Okay. So this is our reaction 2, that the amount of iodine that is formed in the reaction 1 is actually measured by this experiment, and this is the iodometric titration. After all of the S2O3 negative ions have reacted in reaction 2, any further iodine formed is detected using the starch indicator. So you have to remember this thing as well, that whenever we are doing the reaction in which iodine is there, then we always use a starch indicator, iodine with thiosulfate. S2O3 negative is a thiosulfate ion. So we always use a starch indicator for that reaction. The following materials are used: 50 centimeter cube beaker containing the correct mass of solid potassium iodide crystals needed to make to 50 centimeter cube of 0.1 mole per dm cube potassium iodide. So it means that the mass is weighed and it is present in the 50 centimeter cube beaker and you have to prepare it. 0.1 mole per dm cube sodium thiosulfate aqueous, zero point 0.1 mole per dm cube hydrogen peroxide aqueous, 0.2 mole per dm cube sulfuric acid aqueous, starch indicator, and distilled water. Okay. So these are the things that are provided to us. A second student looked at the equation for the reaction 1 and stated that order with respect to the concentration of iodide ion must be second order because the balanced equation contains 2 moles of iodide ions. Suggest why a balanced equation alone cannot be used to determine the order of a reaction. Yes, who is going to suggest? Just that's what we have discussed in the reaction kinetics as well. Can anyone remember?
It depends on the slowest reaction.
It depends upon.
The slowest step.
Yeah, that is for the mechanism. But we cannot find the order experimentally, because you have to find the slowest step of the mechanism. You have to perform the experiment and you have to, record the time for each step, that what time each step is taking, right?
Yes.
So order of reaction, or you just write order because it's not the order of a reaction, it is order with respect to iodide only. So order can only be determined experimentally. You can't determine order without any experiment. Okay, so you have to remember this thing, that you have to do the experiment and you have to record the observations per unit time, and then you can conclude the order. Otherwise, you can't determine the order. Now, B part. Describe how the student makes 250 centimeter cube of 0.1 mole per dm cube potassium iodide aqueous starting from the sample of a solid potassium iodide in 50 centimeter cube. Give the name and size of any key apparatus used. Describe how the student ensured that volume is exactly 250 centimeter cube. You may wish to write your answer using a series of numbered steps. Okay, so what would be a key apparatus when you have to prepare a solution? I have discussed it earlier so many times. Yes. Yes, who can answer? In which apparatus, in which glassware we prepared, solution?
Volumetric flask.
Volumetric flask, very good. So we always use volumetric flask. Okay, so there is a solid in 50 centimeter cube of a beaker. So what you will do first? Dissolve solid in a small amount of distilled water. Then transfer it to volumetric flask. Okay, then transfer it to volumetric flask. Now wash the beaker and transfer the washings to volumetric flask as well. It is because to make sure that there is no traces or not a single or a very small amount of potassium iodide would be left. So we transfer all the washings in the volumetric flask as well. And afterwards, what we will do? Okay, I have just forgot one thing. You have to keep write the volume capacity as well. So it to mention over here 250 centimeter cube volumetric flask. Now, fill the volumetric flask up to the mark with distilled water. Is this part is clear to everyone? Yes.
Sir, did you dissolve in the beaker?
Sorry.
Did you dissolve the solid in the beaker?
Yeah.
Right.
Because it is in the 50 centimeter cube of a beaker. So if we, for example, fill it till the 50 centimeter cube, it would be lower than the amount because we have actually prepared, we have to prepare it in 250 centimeter cube volume. Okay. Now, the student carries out experiment one using the following steps. Okay. 25 centimeter cube of 0.2 mole per dm cube sulfuric acid to a conical flask. Okay. It's a volume and the concentration. Add 20 centimeter cube of a distilled water to the conical flask from a burette. Add 5 centimeter cube of 0.1 mole per dm cube potassium iodide to the conical flask from the burette. So here we have a concentration and volume of potassium iodide. Add 5 centimeter cube 0.1 mole per dm cube of sodium thiosulfate to the conical flask from a burette. Add 2 centimeter cube of a starch indicator to the conical flask. Okay. Use a burette to add 10 centimeter cube of 0.1 mole per dm cube hydrogen peroxide aqueous to a small beaker. Okay. Add the content of the beaker to the conical flask and start a timer immediately. Stop the timer when the starch indicates the presence of iodine. So when the starch, remember that starch forms a blue-black complex with the iodine. So when that blue-black complex would appear or the solution turns blue-black in color, then we, stop the timer and record the time. Okay. Now, the student carries out further 6 experiments by repeating step 1 to 7 using the volumes in the table 2.1. So in each experiment, they have changed the volume of distilled water and the potassium iodide. Okay. The rest of the 2 volumes would be same. State how the student could improve the reliability of the experiment. Yes, how could the reliability can be ensured. So we can repeat the experiments and take average. So each experiment is repeated with the same volumes and note the time and then take the average of the time. So repeat the experiments and take the average. Okay. State the independent variable in experiments 1 to 7. Yes, in these experiments 1 to 7, what is independent variable? Yes, who can answer me?
Sir, potassium iodide.
Just potassium iodide? You must have to mention
And
the
water.
quantity. Volume of potassium iodide,
Oh, sorry.
not just potassium iodide. Volume of aqueous potassium iodide, that is V. Why? Because we are actually changing these volumes, and due to this, the concentration of potassium iodide is changed. And due to the change in concentration of potassium iodide, we are getting these results. So these are actually dependent variables. This is the dependent variable, and this is the independent variable, because it is one which we are changing on our own will. Okay. So in experiment 5, the starch indicator changed color immediately on adding hydrogen peroxide. The student realized an error had been made. Suggest which step is missed in experiment 5. So here you have our steps. Now, what step you have missed? Because on adding H2O2, the color changed immediately. So, okay, look at over here. What they are saying, you read this statement, that after all of the S2O3 2 negative ions have reacted in reaction 2, any further iodine formed is detected using starch indicator. So it means that whenever there is a starch and thiosulfate both in the solution, first thiosulfate is going to react, and then in the second stage, starch would going to react with iodine, and here the color is changed readily, quickly as adding H2O2. So it is clearly indicating that this step is missed, that there is no Na2H2O3. And that's why when we added hydrogen peroxide, uh, the iodine formed quickly react with the starch to and shows the color of the complex, starch iodine complex. Is this understandable?
Yes, sir.
So in experiment number 5, so it is step 4. Now, the rate equation is represented by as rate is equals to rate constant times concentration of iodide raised to the power n. Okay. Concentration of iodide is proportional to the volume of potassium iodide. Yes. And is the order of the reaction with respect to iodide. Rate is proportional to 1 over T. And log rate is equals to log K plus n log concentration of iodide ions. Okay. Use the results from the student's experiment in C to complete table 2.2. V is the volume of potassium iodide aqueous and T is the time taken for the color to change. Give all the values to 3 significant figures. Okay. So first take log D. Yes. Take the log of V. And when then we have to take the log of 1 over T as well.
Sir, 0.699.
0.699.
699.
Okay. Then
1.
1. So if the examiner says you to write in 3 significant figures, so you must write 1.00. Okay.
Yes. 1.0.
Part
1.097.
1.097. So it must be 1.10 as a 3 significant figures.
1.18.
1.18. Okay. Then
1.30.
1.30.
1.40.
1.40. Okay. Now log 1 over T.
Minus 2.41.
Minus
2.41.
2.41.
Minus 2.08.
Minus 2.08.
Minus
Yes.
2.05.
Minus 2.05.
Minus 1.88.
Minus 1.88. Next.
minus 1.75,
minus 1.75,
minus 1.64,
minus 1.64. Okay. So the examiner is asking plot a graph on the grid to show the relationship between log v and log 1 over t. Use a cross to plot each data point, draw a line of best fit. Okay. So 0.0699 and minus 2.41. So minus 2.41 would be over here, and it's 0.699. So it must be over here. Then 1 and 2.08. 2.1 minute. It's 2.41. Okay. So this point must be over here. And then can anyone tell me the points? Minus 2.21 was there? Yes, in a second row.
सर मैंने लिखी नहीं है, अगर किसी ने लिखे हैं तो वो बता दे.
1 and minus 2.08. Okay, so minus 2.08 would be over here. Minus 2 and 2.08. And it's a 1. Okay. Then 1.1 and 2.05. 1.1 and 2.05. So 2.2 and 2.05 would be over here. Then 1.18 and 1.88. 1.88 and 1.18. So it would be over here. Then 1.3 and 1.75. 1.75 and 1.3. So 1.75 would be over here. And then 1.4 and 1.64. So minus 1.64 and 1.4. So it would be over here. And we have to draw a line of best fit. Okay. So this would be your line of best fit. Now in part 3, a timing error caused the most anomalous point on the graph. Circle this most anomalous point. Okay, right now, the most anomalous would be this one. Right? So the volume is this, but in actual, this point or this time would be at this volume. So it means the volume recorded is lesser than the actual volume. Okay, 1 minute. Here they have asked you to explain the error in timing which led to this point. Okay. So instead of this, the log 1 over t would be over here, which would be lower. So I can write that the actual time is less than recorded. Okay. Now, fourth part. Use your graph to determine the gradient of the line of best fit. State coordinates of both points you used in your calculation. These must be selected from your line of best fit. Okay. So we have to take 2 points on the line. Yes, can anybody help me in that? So what are the coordinates of this point? Minus 2.22 on y-axis, and on x-axis it would be 0.92. So 0.92 and minus 2.22. Now, the next point. Can be this one. On y-axis, it is, on x-axis, it is 1.22, and one y-axis, it is 1.86, minus 1.86. So 1.22 and minus 1.86. So the gradient would be minus 1.86 minus 2.22 over 1.22 minus 0.92. Yes, can anybody solve the gradient? Yes.
1.2.
1.2. Is there any number after 1.2?
No.
So we will write 1.20. Okay. Just let me check. Minus 1.86. Okay, that's fine. Now, okay, last part. The total percentage error from the measurements is determined to be 5.25%. Okay. The true order of a reaction is 1. Use this and your gradient from D1 to determine whether the error in the experiment could be accounted for by error from measurements or is caused by other factors. Show any working. So if we would be able to justify order 1, then the experiment error could not be accounted, or otherwise it would be accounted. Let's see. The total percentage error from the measurements is determined to be 5.25%. Okay. Use this and your grade from D4. Where is the gradient? Okay. Gradient is 1.20. Yeah, okay. So the total order is what? 1. The gradient is 1.2, right? This is my gradient. So how can I find the error? My gradient is 1.2 minus 1 because the order is 1 and the total order is 1. So I would keep 1 in the denominator and times it by 100. Can anybody tell me the answer? What percent I'm getting?
20.
Okay. So I'm getting 20%. See, which is a bigger value than 5.25. And they have said that the total percentage error from the measurements is determined to be 5.25%, but the error is more than that. So I can conclude or comment that there are other factors as well which cause the error besides the measurements. So I can write that there are other factors as well which caused the error. Is this clear to everyone? Because if this error, what I did, I subtracted it from the gradient to get what is the difference in the actual order and the order that we have calculated over here. And then divided by the total order that is given to us is 1. And then times it 100 to get the percentage. And our percentage would be very higher than the actual percentage of the measurements, actual percentage error of the measurements, which is clearly indicating that there are other factors also there which is actually causing the error, not just the measurements. Okay.
So why did we subtract it from 1? Why did we subtract 1 from it?
Because it would be the change, it is the difference, right? Because
So what is 1?
This is, but one is the order that they have given to us, and this is the value that we got for the, see, they said that you have to use the order that is 1 and use your gradient from D4 to determine whether the error in the experiment could be accounted for by error from the measurements or it is caused by other factors.
Sir, so we subtracted the order of reaction and also divided it by the order of reaction.
We find see. The thing is that this is the total order, right? 1.
Yes, sir.
And to find the error, we must take the difference. The actual order is 1, and we are getting this value instead 1. So,
yes, sir.
Subtracted, we got the difference that how much our result is deviated from the actual one. So we got that in numerator, the difference from the total, and the total comes in the denominator, and then times it 100. So we get the error, that how much error we are getting.
Okay, sir.
Is it clear, or still if you have any confusion, do ask?
No, sir.
Okay. If anyone else have any confusion, do ask, please. Okay, then take care, everyone. Allah Hafiz.